Alright, welcome back everybody. In this video we're going to start talking about section 9.4 of AP Calculus BC, defining and differentiating vector-valued functions. I've got a lot of expository information in this lesson, some of which you might know, some of which you might not know, so let's kind of dive in and just take a look at what all we say here. So there's a lot of quantities that are represented by directed line segments. Most people know those directed line segments as vectors. Directed line segments are line segments with an arrow at the end to represent the direction of the action. So for instance, you see one of these directed line segments here with initial point A and terminal point B, which goes from there to there. Its length is denoted by, and we can use absolute value symbols. More commonly, we're going to use a double bar to represent the magnitude. You might see either of those. I think this one's probably becoming a little bit more common. Directed line segments that have the same length are equivalent no matter where they begin. Okay, so a directed line segment that starts here at A and ends here at B. If I have another directed line segment that, man, I did a really poor job of getting that to go in the right direction. I missed by a little bit, but that should be parallel to this one. If it goes the same length in the same direction, those two are equivalent no matter where they begin. Alright, a vector in a plane is represented by a directed line segment. Two vectors are equal if they have the same length and direction. We just talked about that. Any vector whose initial point is the origin is in standard position. That's the vector that we normally use to represent all of the vectors that have that same magnitude and direction. And we can just kind of move those vectors around in the plane, but they're all represented by the standard position vector. Component form of a vector. If we have a vector in the plane that's got initial point 0, 0 and terminal point v sub 1, comma v sub 2, the component form of the vector is what you see right here, v equals, and we've got the little angle braces to represent the component form. The coordinates v sub 1 and v sub 2 are the components of v, and the magnitude of v, or its length, again, also represented with the absolute value bar. You might occasionally see the double bar. I mentioned that earlier. But we can find the magnitude of any vector by taking the square root of the squares of its components. Okay, so simple enough so far. Let's look at our first example. We're going to find the component form and the magnitude of vector AB. If A is the point negative 2, 6, and B is the point negative 4, 3. Now there's a lot of ways I can do this. I could translate my initial point and move it to the origin, and then move this point the same amount in the same direction, and that would give me the component form. So that's one way that I can do this. The other thing I can do is I can take the coordinates of the terminal point of the vector and subtract away the coordinates of the initial point of the vector, and that'll give me the components of the vector. Either way, there's a couple of different ways that I can handle this, so I'm going to go ahead and I'm just going to take the coordinates of the terminal point minus the coordinate of the initial point. Oops, my brain exploded there for a second. Terminal point coordinate minus initial point coordinate. And if we simplify all this, it gives us the component form of this vector, which is negative 2, negative 3. So that's my component form. The magnitude of this vector is its length, which we are going to get by taking the square root of the squares of the components. And if we do all that, we end up with the magnitude being square root of 13. All right. Writing vectors. So if you see vectors in books or online, a lot of times you'll see them denoted by lowercase or bold-faced letters. It's hard for us to write boldface by hand, so you might see vectors with arrows. You also might see vectors with hats. They tend to use those a lot in your physics classes. But really any of these might be ways that we represent vectors. Sometimes when I'm typing them on my computer, I sometimes type them in boldface with an arrow. So you know there's a lot of different ways that we can represent and write vectors. When we start talking about vector-valued functions are functions where each of the components of a vector are in essence, a parametric function. Okay? And you can see these and how they're written in a lot of different ways. We've got component form here of the vector R. And that vector has, as each of its components, a function. X as a function of time, y as a function of time. This might be what a vector-valued function looks like in component form. By the way, component form is the form that we typically use on the AP exam, so I'm going to use that one far more than any of the others. Unit vector form, where we multiply them by the basic unit vectors. By the way, the vector I is equal to the vector with components 1, 0, and the vector j is the vector with components 0, 1. I know you see those in your physics classes sometimes, at least those of you who go to my school see those in your physics classes sometimes. So that's another way that we can write this same vector. These two things are identical in meaning, the component form and the unit vector form of these two expressions. And then of course there's just a parametric equation form where sometimes we write this as a position function as a point. This means, the same thing. We are going to use this form probably 90% of the time, use this form probably 9.9% of the time, and then this form I'm barely ever going to use. All right. Next thing about first thing really about vector-valued functions. When we're talking about vector-valued functions, the domain of a vector-valued function is the intersection of the domains of the components of that vector-valued function. So for instance, suppose I had this vector-value function written here, r of t, written in component form, and I wanted to know the domain of this vector-valued function. Well, the domain of this vector-valued function is going to be the intersection of the domain of its components. We talked about this very briefly when we were talking about parametric equations, how the domain of a parametric curve, the time values where the parametric curve existed, was the intersection of the time values where the individual parametric equations existed. Same thing's going to happen here with a vector-valued function. You'll find there's a lot of connections as we go through vector-valued functions. There's a whole lot of connection between vector-valued functions and parametric curves. So we're going to find the domain of this. The domain of 1 over square root of 2t minus 3 is a domain of, let's see, t has to be greater than 3/2. And for the natural log of the quantity t plus 1, the domain is that t has to be greater than -1. And so if you think about where these two domains overlap, they overlap for t greater than 3/2. And so that's going to be the domain of our function. T is greater than 3/2. Just going to keep plugging until I'm almost out of time. The limit of a vector-valued function. If we have the vector-valued function r of t here, if the limit as t approaches c of the first component is L sub 1, and the limit as t approaches c of the second component is L sub 2, that means the limit of this vector-valued function is the vector L with components L sub 1, L sub 2. So if I want to find the limit as t approaches 2 of r of t, if that's my vector-valued function here, this is going to be equal to the limit as t approaches 2 of 2t, which we can just find is 4, and the limit as t approaches 2 of 3t minus 1, which is just going to be 5. And so the limit of this vector valued function r is the vector 4, 5. The limits of vector valued functions are vectors. All right. Keep plugging away. Continuity. Here we talk about continuity of a vector valued function. If we have a vector valued function r of t, it is continuous at a real number c if, and I even wrote a note here at the bottom. This should look really familiar. Way back in Unit 1 of AP Calculus, we talked about the 3-step test for continuity. This is identical to the 3-step test for continuity. Instead of it being for a Cartesian function f of x, it's for a vector valued function r of t. So the vector valued function needs to be defined at the real number. The limit, as t approaches c, of the vector valued function needs to exist, and those two values need to be equal to one another. That should be a c there. I don't know, that's a typo. Okay. So that's continuity. If we ever need to determine if a vector valued function is continuous, we can do this. So basically we're just building all this stuff that we did way back in the beginning of the course with functions. We're building it up now with vector valued functions. All right. Derivatives of vector valued functions. Again, I made a little typo. I'm missing a prime there. So to find the derivative of a vector valued function, if r of t equals the vector valued function with components x of t and y of t, and if x of t and y of t are both differentiable real functions of t, then r prime of t can be written as dr dt with the component forms x prime of t, y prime of t, or same thing, different notation, dx dt, dy dt. So in order to find the derivative of a vector valued function, all we're going to do is take the derivatives of the components. Let's go ahead and we'll start example 4 here. We're going to find the derivative dr dt if the vector r of t is has component 1 over t squared plus 1 and t over square root of t squared plus 1. So vector r prime of t is going to be a vector with 2 components, and now we just need to figure out what those components are. So I'm going to start by taking the derivative with respect to t of 1 over t squared plus 1. Okay, and that's going to be, let's see, that's t squared plus 1 to the negative 1. So it's going to be negative 1 times t squared plus 1 to the negative 2 times the derivative of the inside, which is 2t. And so that all simplifies to negative 2t over the quantity t squared plus 1 quantity squared. So that's going to be my first component of my vector. And my second component is going to be the derivative of t over the square root of t squared plus 1. So again, we're going to have low d high minus high d low here. Don't want to do it that way. No, I'm going to think about this as, do the product rule. This is going to be t times t squared plus 1 to the negative 1/2. I'm going to go ahead and take the derivative that way. And so this is going to be t times negative 1/2 quantity t squared plus 1 to the negative 3/2 times 2t plus t squared plus 1 to the negative 1/2. So that all simplifies to 1/2 and the 2 cancel each other out. Negative t squared over t squared plus 1 to the negative 3, or to the 3/2, plus 1 over t squared plus 1 to the 1/2. To get them over the same denominator, this becomes negative t squared plus 1 all over t squared plus 1 to the 3/2. And so this becomes 1 over the quantity t squared plus 1 to the 3/2. And there's our derivative of our vector valued function r. We're just about out of time, so we'll come back and do part B and the rest of this lesson in our next video. Have a great rest of your day, everybody. See you next time. And I'll talk to you when I'm talking to you. Bye-bye.